Hey, howdy everybody. So the smoke is cleared, the grades have been submitted, the course is done, and so I had a little bit of breathing space right now to go ahead and record the final lecture from the course. Now this is mostly a fun lecture, kind of a fun discussion that I shared with the students, and I thought maybe other people might be interested in it, so I'll just record it and put it online just in case. So, some concluding thoughts from the class. And so this discussion is going to be around what have you learned in this course and how could you use it to add greater value, to differentiate yourself from other geoscientists and engineers. And so in my 13 years that I spent in industry, I met two types of people when I was dealing with the different types of problems in data analytics, geostatistics, and statistical learning. And what I observed was there were those people who found these geostatistical problems and wondered how you could solve them. Would sit there and go, boy, that would be very cool if we could solve those problems. And then there were those people who understood about data analytics, geostatistics, statistical learning, and were able to solve those problems. Were able to teach other people how to solve those problems and made tools that solved those problems and were widely recognized for that work. Geostatistical problems, spatial data analytics problems, spatial machine learning and statistical learning problems are everywhere in subsurface resource characterization, modeling, and development. Spatial temporal, univariate, multivariate, sampling, inference, prediction, all of that is everywhere, all over our industry. So here are some of the topics that we covered in the class that I'm suggesting could immediately have impact for you when you get out there in the field. So the first thing is use all of that fundamental probability math. Keep that. Those fundamental probability rules are very powerful. Remember we talked about the addition rule. When you have two different events, you're adding them together, but in fact there is an overlap between the events. The addition rule suggests that the union of the two events occurring, you have to subtract the intersection or you will double account for that. That will create a bias in your probability. And so you may even have a probability that's not in fact physical. It may be exceed 1 and so forth. And so there are many times that you're going to find situations where we need to do this, to find unions of events. We're considering multiple criteria. We're trying to model and subset data and so forth. And so we're going to be needing to work with these types of unions. Make sure that we rigorously account for the probability calculations. If we don't, we will significantly bias our assessments of probability, and that can lead to some bad decisions. Also, remember what we talked about when we're talking about the joints and the marginals and the conditional probabilities and how they all fit together. In fact, there may be occurrences when you're dealing with a lot of data. You have a dense sampling of your problem, and you may find that you actually have enough data available to you that you can directly calculate the marginals, the joints, and the conditional probabilities directly from the data itself. That is extremely powerful. We can answer all kinds of questions from using these probabilities directly. So you could consider, for this example right here, we may be concerned about the probability of a certain rock property given a geophysical response. Well, you could use a Bayesian formulation to get at that. What we're effectively doing is we're avoiding the use of a joint probability because it's hard to calculate that from data. But if you have dense data available to you, you may in fact be able to calculate that joint probability directly from the data itself, and so you don't need to use the Bayesian updating approach. You can go ahead and go directly to just counting. In other words, you may already have the answer if you have dense enough data to work with, and that may happen in some cases where you're running many experiments. Check for independence. We talked about how we can check for independence with data sets. In fact, what would we expect as far as the joints and the conditional probabilities with regard to whether or not we have independence or not. In the example that we showed in class where we're talking about certain proportions of facies given different units within the subsurface, it's pretty important to know whether or not there is a relationship between the location vertically or the units within the reservoir and the proportions of facies. Well, we can check and see if with the amount of data we have available to us, if it makes sense, if in fact it appears to be independent or not. If we see that it appears to be independent, we may make a decision to just model the whole thing together and save some time. If it appears that it's not independent, then of course we may break it up and we may find that we in fact have more information now. We can further constrain our uncertainty models. Independence, simpler workflows. Not independent, we're using valuable information. Check for independence. Bayes' theorem. Well, we know there's times in which we need to go to Bayes' theorem. There are some difficult problems where we're unable to directly assess the specific conditional probability we need. Remember that example of what's the probability that something is happening given it looks like it is happening. Well, that's very hard to calculate. We gave a whole variety of different problems, such as you test positive for disease. Do you in fact have disease? This is a very valuable methodology. Now, when I showed this in a video, of course, on YouTube, there was some really good feedback, and the feedback was, well, what about the idea of value of information? And that's totally true. If you look at the difference between the prior probability of something happening and the posterior probability something's happening, given it looks like it's happening, that in fact is a measure of the value of that information, that test that indicated that it looks like it's happening. If those probabilities are different, it tells you in fact have received a significant update in your assessment of probability, so that information may be valuable just from the perspective of value information. There's a lot that we can talk about as far as Bayes' theorem goes, but of course it was a very useful and very powerful tool. Okay, statistical expectation. Just remember how statistical expectation acts as a linear operator. In planning and decision making, expectation is used all over the place. They talk about the management will make decisions based on the expected net present value and so forth. And so if you understand how to work with expectation as an operator, you can solve important problems with regard to the expected profitability of an operation or other expectations very quickly, back of an envelope, and you can provide insights very quickly in order to support decision making directly. Remember the concept of Monte Carlo simulation. You can use Monte Carlo simulation all over the place. It's very powerful. You can use it on any transfer function or equations. You can use it on any distribution. You can use Monte Carlo simulation to propagate uncertainty from the inputs through to some outputs, understand sensitivities and so forth. This is an example paper that came out just last year, or this year actually, in fact. Co-authors including Jake Kowalt from over at the Bureau of Economic Geology, right next door to us here. And what we found was we could analyze and understand the uncertainty models with regard to what sediments are getting deep into the Gulf of Mexico, given some constraints about what was happening over geologic time as far as the discharge rates, the catchment areas, and other types of parameters with regard to the basin relief and other types of factors. And so this is a very powerful tool. We can use Monte Carlo simulation to understand uncertainty in complicated problems. Also, don't forget the Bootstrap. That's super useful too. Uncertainty in any statistic from the sample itself. Very powerful. Okay, heterogeneity, measures of heterogeneity. Heterogeneity is critical to, I would say, any spatial problem, but especially in the subsurface. Here's a nice little example here, taken from this publication right here, Hampson 2012. We have an injector, we have a producer, and we see blue here. Blue is indicating on a 4D seismic response that we have hardening. Oil is being replaced by water. What's this telling us? Is that we have a pipe of high permeability. Perhaps it's a deep water channel. That's what I think it might be. And we can see that we are in fact causing a short circuit. We're not getting very good sweep of the reservoir. That's because of heterogeneity. Remember the measures of heterogeneity and use them. Some of the measures of heterogeneity, you can just go ahead and calculate them directly from the distribution. Others you need to line up along the well, the porosity and the permeability. And when it came to Lorentz coefficient, we had to calculate the cumulative storage capacity versus the flow capacity to calculate it, but still very straightforward and still is a very useful predictor. Selecting analogs and making some type of a fast assessment of the impact of heterogeneity on your performance of your reservoir can be very useful. Uncertainty confidence intervals on everything. Every time you show a statistic or a plot, think to yourself, could I put uncertainty on that plot? It matters. If I showed this plot without the confidence interval, the 95% confidence interval is shown here by the dashed lines, you may wonder whether those wiggles are important or not. Well, given the confidence intervals are this wide, those wiggles are probably not important, but the trend is important. That gives you context. In fact, another way to think about it is that decisions up at upper level management, mid-level management for development of reservoirs is going to be based on uncertainty models. P10, P90, the mean, the P50, measures of uncertainty. If you put uncertainty on everything you do, your work can be communicated directly to the decision makers and you directly impact the decision. The limits of the correlation coefficient. Correlation coefficients are everywhere. Remember the issues around outliers, the sensitivity of the Pyrcz correlation coefficient to a single outlier, and remember the use of the Spearman, the rank correlation coefficient, to try to get a more robust one in the presence of maybe some slight nonlinearities, or maybe in the case where you have an outlier. Correlation coefficients are everywhere. The Bootstrap. I mentioned the Bootstrap before. I forgot I had the slide. Okay. If you got a sample statistic and you need to add uncertainty to it, use the Bootstrap. Bootstrap is very powerful. You can calculate it on any statistic. It would be very difficult to do that using an analytical approach, but we can do it just by resampling with replacement from the sample itself. Assumes representativity of the sample. You have to have enough samples that you actually have a pretty good understanding of the distribution, statistics, and so forth. But it's very powerful. In this example in Excel, we showed that we could add uncertainty to the min, the max, the P10, the mean, P13, anything we want to add uncertainty to. Keep stationarity in your back pocket. Anytime you're working with spatial data, in fact, I'd say even temporal data, but spatial data, you have to understand the import and the export license. What data was pulled together to calculate a statistic, and where can you now use that statistic as a predictive model? Any statistic that you work with spatial data will have this built into it, cooked into it. And so you should always ask that question. Remember the brick wall in the discussion about stationarity. Spatial continuity, calculate it, use it. If you're working with time series analysis, you could look at autocorrelation or the Pyrcz coefficient. Very easy to do. Interpret it as a set of nested spatial or temporal frequencies. Use each of them to provide you with prediction over distance. There's a range. There's potentially a nugget effect. There's going to be a sill. We can use that to make predictions and understand what's going on spatially, to compare analogs to each other, and perhaps relate it back to other important types of factors like heterogeneity and impact on recovery, or any type of transfer function in the subsurface. We can take spatial continuity and we can make predictions in space. We can do spatial estimates, and we will be careful with them, because we remember that they're too smooth, they don't reproduce the right variability nor the covariance between the estimates, but they can still be used. The great thing about kriging is it provides you as a good friend, a good honest friend. It provides the best estimate at each location, given stationarity and the spatial continuity model, but it also tells you how bad that estimate is. A map of the kriging or estimation variance is provided to you. So you can identify new locations you should drill to reduce uncertainty, or locations where the uncertainty is low and you have a better chance of success. You can do pre-drill estimates using kriging. You can also go ahead and try to assess volumetrics, map out resources that are available and remaining to you. It's pretty powerful. But when it comes to any type of flow simulation or any type of methodology or transfer function, I should say, that requires heterogeneity, use simulation. Simulation will provide you with the heterogeneity that may impact the response of the transfer function. Now, you may not need simulation if the data spacing is very small relative to the size or scale of the heterogeneity. In that case, the data may impose the heterogeneity sufficiently, and there are reservoirs around the world with dense data that just use spatial estimation and they're fine. Now remember, if you create multiple realizations and scenarios, use each one of the models for every one of your questions. Retain the models, use them all for every single question. Know about machine learning, statistical learning. Understand how they work. Many of them are based on intuitive natural examples, and so they are quite intuitive and they are logical to us. Decision trees, the hierarchical binary branching approach. A lot of people say that there's cognitive scientists who say that that's in fact how our brains work. Artificial neural nets, of course, it's an analog model that's based on our brain. Swarm optimization, based on the idea of swarm intelligence. Simulated annealing is based on the idea of metallurgical annealing. So they're logical and they make sense, then they're fascinating that we have systems mirroring or based on natural systems that actually do a good job solving problems. Remember, machine learning is statistical learning. It's still statistical. Understand its limits, its assumptions. If it's non-parametric, it really means parametric rich. It means there's a lot of parameters. There's thresholds and functions and truncations and so forth. Remember this concept of the expected test mean squared error, that there's a complexity trade-off. Greater complexity means greater model variance, less model bias, and irreducible error. You can't model your way out of it. So now what? What's my recommendation right now? We finished the class, we're done here together. Well, stay current. There are many resources available to you. I think we live in a time and age where there's almost like no excuse not to be current. It's so available to us. There's lots of good open source. The world is sharing its brilliance with us. Let's use it. Python and R. Many online courses are available to you. There's so many ways to get great instruction and demonstrations and new ideas available online to you. Conferences and journals, participate in those. Consider reviewing publications in a variety of open journals or in the regular journals, and podcasts, meetups, blogs. Participate in social media. More voices to support good scientific methodologies, understanding of sound statistical probability concepts would be useful to everybody. So right now I'd like to pay homage to the mentors that helped me along. I spent 13 years in industry. I very much enjoyed my time in industry, and I was very much helped and guided by so many great individuals. And I just think that this is some really nice advice that I heard from some of these individuals. And so there was an amazing division manager, and they reminded us, or this manager saw that I was overloaded with work and I was just busy all the time and spending too much time in the office, came in my office, sat down and said, "Michael, in life you are juggling 3 balls, So you're juggling these 3 balls. And he said the balls are work, your health, and your relationships. And he said the work ball, it's a rubber ball. And the other 2 are made of glass. And so if you're juggling and you can't keep up, you can drop work and let it bounce. Grab it and keep going. The other 2 balls, you don't get to drop them. Okay? I thought that was just wonderful. There was a great stratigraphy team leader who mentored me along much of my career, who reminded us that if it doesn't get in the model, it doesn't matter. We need to take our expertise and assure that it gets in the numerical models so that it'll impact the forecast and then impact the decision making. It was a challenge to be even more quantitative to ensure that we got our knowledge into the models. There was a unit manager who told us that you add value when you impact a decision. If what you do doesn't impact the decision, then you're not adding value. So you have to, everything you do should be around decision support in the business. There was a really cool research leader who told us that there's many complicated methods to tell us what we already know. In other words, perhaps we should look at simpler methods. Use the principle of parsimony. If there is a way to learn something doing it in a simple manner that's more understandable, that can be beneficial. And if we're going to be more complicated with our approach, we should first try it in a simple manner so we can baseline, we can compare and see the incremental value of the complexity. There's a complexity trade-off, of course. The same stratigraphy leader told us we should find the difference that makes a difference. Just because something's different doesn't mean it should be something that we all focus on. We need to look for those differences that have the biggest difference in the outcome. Sensitivity studies, understanding what might be random effect versus something that's really diagnostic and important to us. There was a team leader who reminded us and reminded myself that your career is a marathon. If you don't take care of yourself, you're not going to do very well inside the company because you won't be around anymore. And I saw that. I saw people who injured themselves because they didn't take ergonomic breaks and they ended up not being able to work that well anymore. All kinds of things happened. And so you've got to take care of yourself too. Find those ways that you can keep yourself strong and keep working through, have a long, happy career, right? There was a retiring mentor who right on their way out the door took me out for lunch and just told me, Michael, it's all about the people. It was the people. It was the people that mattered. And I found that very touching. We had a world famous seismic geomorphologist who used to remind us all the time that they wouldn't have seen it if they didn't believe it. Be aware of our own cognitive biases. How does that impact our decision making? What we see, our interpretations, be aware of that. And there was a great advisor, in fact my PhD advisor, who always reminded me the way you're valued in an organization is proportional to the way you are valued outside of it. Stay externally visible. Don't disappear inside an organization. Continue to contribute to the scientific community and build a network everywhere, not just inside the side of the organization. There's a lot of other good quotes I could have brought up, but I thought those are kind of at the top. My quote would be, enjoy the venture, it goes fast, stay positive. Take no offense. When it comes down to it, enemies are expensive, friends are valuable, and there were plenty of people along the way I could have been offended by the way they treated me. But in the end, years later, they were very helpful to me. Everybody's got things going on. Just take no offense. Be flexible. Learn new things. Opa used to tell me on the farm when I was a farm kid, I used to say, well, I've never done that before. And Opa would say, well, it's about time you learned how, and that was the approach on the farm, is you just learn how to do it. Have that same attitude. Hey, I'll learn it. That's something I can learn. It's all just like mountain biking. Stay nice and loose on your bike. Pick a line. Focus on the line. Don't look at the route. Don't look at the hole, or you'll ride into it. Focus on your line and roll through it. It's great. Now, one thing I told my students at the very end was I said, you know, we're all in it together. There's a great network. It's in our professional community, in the school you come from, those you interact with. During my course, the door was open. My students were welcome to come in any time, and I was always happy to discuss with them. In fact, I told them in class it was kind of selfishness on my part, because otherwise my job would be to sit in an office by myself and write proposals that ultimately get rejected. And so it was probably better for my psychological state to fill some meaning by having students punctuating that with great questions and explaining science to them and doing why I'm here is to be an educator and to do research. So interacting with the students. I told them if you got a geostat problem next year during an internship, during a senior project, or even after you graduate, come and talk to me. I'd be happy to discuss any time. I'm always happy to talk geostats. You want to bounce a stats question off me from your office in Houston, Calgary would be awesome, Stavanger, wherever you end up in the world, go ahead and do it. And so really I do appreciate the students. It was my joy to be able to work with them. I was glad that they were very understanding and they provide excellent feedback and ideas. I learned a lot from this class. It was only the second time I taught it. And of course there's lots of stuff we're still learning. I'm still learning about how to educate and how to teach. I told them I'm going to keep sharing information, the course notes and so forth, the workflows, it'll all be evergreen. You can go back to it anytime and learn more. I'm available also on social media, Twitter, and here's my GitHub repository. And so I put everything out. And the slide that I used at the very beginning of the course, I think at the end of the first lecture, that's how we end it, because there's never an ending. It's just a new beginning. It's just new opportunities and so forth. To anyone who's observed this course during the entire term, thank you very much for participating. This was a bit of an experiment. What happens if you put every one of your lectures and all your resources out online? And in general, what happened was, boy, a lot of good feedback. I ended up in debates and discussions with German statisticians or people from all over the world with their feedback and improve the course notes. It probably helped me polish the delivery because I had to practice doing it in video before I did it in the lectures in class. And I think it will be a resource for my students moving forward. I hope so. And I hope that this has been helpful to other people even outside my course. I am always happy to discuss. I am Michael Pyrcz, a professor at University of Texas at Austin. Super easy to find my contact information. And I'm also Geostats Guy on Twitter, so you can reach out to me through Twitter, Facebook, LinkedIn, or anything like that. All right. Thank you very much. Take care.